Welcome back for this online session. So in the previous class, we have discussed about the uh, post-order traversal. So in this class, we'll talk about the level order traversal. So level order traversal, okay, coming to the depth first algorithms like pre-order, post-order, or in-order traversal, we follow recursive methods. Okay, we use the recursive method to traverse, but in the case of level order traversal, it's not possible to traverse the level order using a recursion. So look at this. The elements are nodes visited by a level from top to bottom. That is what the level order traversal says. So you have to traverse from level by level from extreme left to right. Within the levels are elements or nodes are visited from left to right. That's what a second point says. It is difficult to write recursion for this level order traversal. That's what I mentioned previously. So we cannot use a recursion to recursion for level order traversal. The correct data structures we use here is what? Queue data structure. So we use queue data structure to perform the level order traversal. Yes, look at this. I think you're familiar with how to represent the level order sequence for this binary tree. So we start with the first level, level 1. So node A is display. Level 2, start with the node B, extreme left one, B. Then you have to display C. Then come to level 3, node D, then E, then F. Then come to level 4, first display node G, then H, then I, and then J. This is how we have to display the uh, sequence in level by level of the binary tree. So let us go through the pseudocode first. Next, we'll go for function. Let t be the tree node, while t is not equal to null. While t is not equal to null, visit t, put its children on the p4 queue. If p4 is empty, then t equals to null. Otherwise, pop a node from the p4 queue and call it to t. So we'll see the code later. We'll understand this easily. Yes, sir. So I take a function that is level order. Return type is void. I use a template variable. So I pass the root address of a binary tree is of type again binary tree node. So I use one queue, that is queue is an object belongs to array queue. So I use the array method to store the address of the left child and the right child. So the queue I taken as a pointer. It holds the address of a left child or right child. So while root is not equal to null, yes, if so root is not equal to null, what we do? First we display the element, that is root of element, right? Then put the root children onto the queue. Nothing but by placing the address of its children onto the queue. Okay, that is queue array queue. So we're checking is the root of left child is not equal to null. If so, what we do? Q dot push root of left child. That is the root of left child is what? It's an address. You're pushing the address into what? Q. Then we're checking the root of right child. Root of right child is not equal to null. If the root of right child, nothing but root of right field of that particular node is not equal to null, we push that right child address into Q. I repeat once again, we are checking the first root is not equal to null. Before that, I have taken one array Q to store the addresses of node. Okay, so if not equal to null, we display the value of that particular node. Once we display the value of that particular node, we check the left link and the right link of the particular node. If it is the left link, nothing but root of left child is not equal to null, we put the left child address into queue. That's what we do push operation by pushing the left child address into the queue. Then we check the right child address, right link of that particular node, nothing but root of right child. The root of right link is not equal to null. If so, you're pushing a right child address into the queue. After pushing both, next what we do? We start front operation. We get the okay, because we are done with the root node. Next, you have to come to second level, extreme. Left child. Left child. You have to start with the left child of that particular node. So how to get the left child address? I do the front operation. So I'm placing in root. Then after getting the front value, we do the pop operation. Remove from the queue. Okay, we'll see the example. So this is my binary representation, linked representation of this binary tree. So I have a root node 2, 4, 5, 8, 9, 10. So I have to I have to write the level order sequence for this. Yes, I have taken one queue, that is a queue where it's set. So what we do is the root is not equal to null. So we have taken one array queue. This array queue is to what? To push the address. Initially front and back equals to -1 because it was empty. So next what we do is check whether the root is not equal to null. Yes, root is not equal to null. So remind the code, root is not equal to null. If so, root of element. That is what 10. So 2. Next we check with the root of left child. What is the root of left child? That is 222. That is not equal to null. Yes, if so, what we do? We have to push this address into queue. Look at this. We have pushed the address of the left child of this node 2 into the queue by incrementing both front and back. So next what we do, this is my queue. Queue is not empty, right? Next what we do, we check the right child address. Nothing but right link of this node 2. What is the right link of this node 2? That is 333, address of the right child. Is it equal to null? No, not equal to null. If so, push the address of this into at the back of the queue. What is the back of the queue? First increment the back, then insert the element. Push the address of right child into this queue. Now we are done with this. Okay, this node. What we did after pushing the right child address, first we push the left child address, then next we push the right child address. So next what we do the front operation. That is q dot front. Root equals to q dot front. Now I have to modify the q. So I have to come to, now we are done with the root. Node 2 first level. The second level I have to start with node 4. Nothing but left child. This is the left child of this node. Okay, node 2. Where the node number 4 address is present. It is present at q, that is 222. Now what we do? Q dot find. What is a q? Okay, root equals to q dot find. Q dot find nothing but get the address into the root. Now root becomes what? 222. Root is equals to q dot friend. What is the friend operation here? That is 222. Q dot friend. Where is friend here? Here. So we copy the address into what? Root. Now what we do? I should pop this. What we do? Popping, erase the element and increment the friend. Now come to root is not equal to null. Again, while loop repeats, is root is not equal to null. What we do? Display the content of this node, that is 4, cout, root of element. Then we check root of left child, left link. The root of left link is what? 444, that is the address of left child, not equal to null. We push the address into this queue at the back end of the queue. That's what we increment the back, push the address of left child into the queue, left child of 4. Then look at the right link of this node number 4, it's not equal to null. It means that what? The root of right child. It has a right child. What is the right child address? That is 555. The right child address of this node number 4 is pushed into Q. That is why we increment, then insert an element, insert the address of the right child. Now we're done with the node 4. Now I have to do the front operation. So I am done with the first node. I have to visit the second node in this level 2. That is what? Node number 5. What is the address of node number 5? That is 333. That's what we do. Front operation. So now root is equals to q dot front. Root equals to q dot front. Now what is the root value now? 333. Now comes to what? After doing the front operation, I should do pop operation. I should erase from this array queue. That's what? Erase this, increment the front. Now what we do is the root is not equal to null. Yes, root is not equal to null. Display the value of this root element. That is what? Root of element. That is 5. Is the root of left child is not equal to null? Nothing but root of left link. Is it not equal to null? No, because it has a left child. What is the address of left child? That is 666. You are pushing this address. That's what? Q dot push 666. That is what we have pushed into Q. Next, we are going to check this root of right child is not equal to null. What we do? We're pushing the address as what? Null. Next, come to node 5, 4 and 5 is over. Now I come to level 3. I should start from node number 8. What is the node number 8 address? That is 444. What we do? I do the front operation. Root is equals to q dot front. Q dot front. Once you copy the address of the q dot front into this root, the root comes to what? Node number 8. Now I should do pop operation. It is done. Pop is done. So next, what we do? We check the root is not equal to null. If so, what we do? Root of element is what? 8. We display it. If the root of left child is not equal to null, yes, no need to do the push operation. Root is root of left child is equal to null. It means that no need to do push operation. Then we check root of right child is equal to null. Root of right child is not equal to null. No, it is equal to null. It means that no need to do push operation. Next, we have to come to node number 9. What is the node number 9 address? That is 555. I should do front operation. Root is equals to q dot 5. What is the front address? What is the front address in that location? That is 555. Root comes here. Now what to do? Pop operation is done. Again, root is not equal to null. Display the value that is CO, root of element, that is done. So root of, okay, left child is not equal to null. No, it is equal to null. No need to push. Root of right child is not equal to null. Is equal to null. No need to do push. Next, you have to get the address of node number 10. What is the address of node number 10? That is 666. It is sitting in what? Q. So we should do front operation. That is root equal to q dot frame. Q dot frame. That is what? 666. Now root comes to what? Node number 10. Now I should do pop operation. If the root is not equal to null, yes, root is not equal to null. So what we should do? Root of element is what? 10. Display. Next, is root of left child is not equal to null? No, it is equal to null. No need to do push operation. The root of right child is not equal to null, or is equal to null. No need to do push operation. Next, finally, what we do? I do the front operation. So root becomes null. Is root equal to null? What happens? So it becomes empty. So let's stop the process. This is how we can do the level ladder traversal for this binary tree. Next comes to what is the arity of this binary tree. I think you are familiar with how to represent the arity of this binary tree. So first instances, collection of elements, partition into root, left subtree, right subtree. Each subtree is a binary tree. And come to operations, we have empty operations. So empty means what? It checks whether the tree is empty or not. If it is true, it returns true. If it is false, it returns false. Size. It returns always returns the size of a cube. Next, we have pre-order traversal operation, in-order traversal, post-order traversal, level-order traversal. So, what is arity of this binary tree? What is meant by arity? So, this abstract data type. It says that gives a specification of this binary tree, and it also represents the operation of the binary tree, but there is no implementation. That is what your arity of this binary tree. And we have mentioned instances, nothing but specification and operations. That is what your arity of this binary tree. So what is the abstract class of this binary tree? To represent arity in using C++ class. That is what your abstract class. What actually the abstract class is? The abstract class nothing but it holds the pure virtual function. So this is my abstract class binary tree, the public virtual destructor. I cannot have a virtual constructor here. So then we have empty operation. So it's a bool. It is return type is what bool because it returns true or false. So again equals to 0 means because it is a pure virtual function. You have mentioned with a virtual keyword. Next I have a size. Return type is int because it always returns size as integer. Size is always a integer. Again the virtual keyword constant operation equals to 0 because it's a pure virtual function. Again pre-order traversal. It always gives the root address. No return type. Again virtual keyword equals to 0. It's a pure virtual function. Again in-order traversal, pure virtual function assigned to 0. Return type is void and virtual keyword. Again post-order traversal, you're passing the root address, no return type, virtual keyword equals 0. Even again same thing for level order traversal, level order function. Yes, these are all okay. Abstract class again it is a representation of this operation, that's all, using a programming language, but there is no implementation. So how to implement all this? We go for concrete class. That is what your linked binary tree. That's what we are implementing your abstract class. So in this case, we require one root node. The root, okay, I have pointer. Pointer to what? Root node is of type again. Binary tree node is of type t, and I have a tree size. That is what binary tree size is what tree size is of type integer. And when it comes to public, so I have a linked default constructor. So assign the root with null and tree size is 0, and I have a destructor. So I don't discuss all this and empty operation. So it checks tree size equals to 0. If it is equal to 0, it returns true. For else, it returns false. Then size, it always returns as tree size. Next, we have a in order, pre order, post order, level adder, and I included one more called as height of a binary tree. By okay, look at this all five operations we are passing root address. I think we have discussed all this in the previous slides, previous classes. So for only one sample I'll give. So I'm defining the pre-order function outside the class belongs to linked binary tree. Return type is what y. We use the scope resolution operator. This is notation for defining the function member function outside the class and passing the root address. So I'm copy this root address into actual root value, and I'm checking the root is not equal to none. So as for pre-order traversal, first, you have to visit the node. That's what display the root of element. That is the visiting a node, root node. Then we have to visit the left subtree. Left subtree, visiting a left subtree means what? You have to call the recursion by passing a left child address and calling the same function. Then after visiting a left subtree, you have to visit the right subtree. How to visit the right subtree? It's again a binary tree, so it should be a recursive function. So I'm calling the same function by passing right child address. I think we have discussed all this in the previous class. I hope you are clear. So next come to how to find the height of a binary tree. Again, we're defining outside the class using a scope resolution operator. And we copy the root address into this actual root. And we're checking a root is not equal to root equals to null. If root is equals to null, the tree is empty, returns -1. So else root okay, and we okay to find the height of a binary tree, I should visit each and every node. That's what. So I take one variable as HL. It is always stores the integer value, and I'm calling and visiting a left subtree of this root node. That is by passing the left shell address. It's a recursion I'm calling again, right? And I've taken one more variable called as HR, that is int HR, and I'm calling again recursive function. I should traverse through the right subtree by passing a right shell address, and I'm comparing if HL is greater than HR, then return plus plus HL, else return plus plus HR. This is how we can find the height of a binary tree. So thanks for watching. I hope you are clear.